please.
All right, thank you. Wonderful to be here with you today. It's perhaps a change of pace for a hadronic physics workshop. So I'll start with some introductions for my assignment to talk about this, how a heavy ion physicist like myself would transition to doing a DIS and where the common ground in this endeavor. So because this is not a heavy ion nuclear physics workshop, so I want to just set up a stage saying a few words about what is it that we usually study. And I decided to frame it in terms of pillar measurements because we talk about EIC pillars so much. So let's be on par. And then my plan is to talk about direct connections between these heavy ion collision topics and what the EIC physics will be delivering. Essentially, it is what we know, what we don't know, and synergy and impact between the measurements that we do in heavy ion collisions and done or will be doing in the DIS, and how they interplay and inform each other. And my wrap up will be another synergy point on the detector developments, but I will be very brief. I cannot beat Elke's talk. So we enjoyed more than 20 years of active experimental research on quark-gluon plasma exploration to understand this strong force and confinement, same goals set up by EIC, but in the deconfined state of quarks and gluons. So what we know from experimental evidence about formation of the quark-gluon plasma in heavy ion collision, that it is a very peculiar matter. It's very hot. The temperatures we are reaching way above the predicted temperature for the phase transition. Its evolution is well described by ideal hydrodynamic, near ideal, but as ideal as you could get for any system we observed so far. And the final system appeared to be not only in thermal equilibrium, but it gets there as fast as you can never imagine. And just the whole medium is very, very explosive. Not only is explosive, but it's at the same time is very opaque to high energy probes, which I also will touch on. So we currently, after many years of studies in precision error for understanding this property, so honing down on the details rather than just the discovery. And this is where we go into the need for detailed understanding of what is it we're starting with, the nucleons and the nuclei, and that by itself is a direct connection to the deep inelastic scattering and the goals of the EIC physics program. So the pillars. Anyone, if they want to describe you quark-gluon plasma in 3-4 slides, would perhaps 90% cases would start with collectivity. It is a big, profound phenomena that we see, as you will see from my talk, in many, many ways. And well, you could see it by a naked eye. So I'm not talking about small, short-range correlation. This is a collective behavior that you see here extending in this two-dimensional multi-particle dihadron correlation across the entire. So all the particles appear to exhibit in collective behavior, which we characterize simply through Fourier harmonics. So we transform azimuthal distributions, and we can relate this final state picture, ignore the jet peak, I'll talk about jets separately, to this global-based picture of initial condition, when on top of this elliptical general form of the overlap region, we have fluctuation, event per event fluctuation in many symmetry planes that result in a complex behavior. You could see these multiple harmonics and colors describing our observed azimuthal distribution of a final state particles. So from the early studies, we observe hierarchies of harmonics. So that is the V2 is the leading term, the strongest, and then we went up to the 6th order. We still see them at the smaller magnitudes. It agrees with the nearly ideal hydrodynamic expectations, and also the estimates of eta over S, the shear viscosity, is very close to the quantum limit. This is why we talk it's near ideal hydro. Now, if you see correlations, even in long-range correlations by themselves, they do not tell you it's a quark-gluon plasma, and that's a mistake like my incoming students often make. Okay, we see the V2. V2 is just the correlations, many things can produce it. How do we know it's something special? Well, apart from the strength of the correlation that, hadronic rescatterings, we quickly realize do not have high enough cross sections to produce such a magnitude. This is another side view of this pillar. When you're looking at the same measurement, so this is the PT dependence of this V2, second order Fourier harmonic coefficient, or V3 that I'll show in the next slide. For different identified particles, we see for a range of energy, so look from 20 to GeV to 5 TeV, we see the same behavior. Mass ordering for different particle species at low PT, if you're looking at that, at transverse momentum. But when you go to the, about 1.5 GeV, the things start grouping themselves together into the baryon and mesons and not the mass. So we see this, what we call constituent quark scaling, which led to the idea that hadronization, the particle production, that V2, the flow that these particles carry, have to happen at the partonic origin, and the hadronization in that partonic partonic hot stage happens through coalescence or recombination. This is how the 2 to 3 peak up of the flow can happen. You can see that even better. Here is another recent measurement. So we simply divide by 2 or 3 if you're dealing with baryon and meson, and plot it as a function of kinetic energy to resolve this mass low PT behavior, mass scaling. And you could see how all these particle species through to charm, open charm D0 hadron, fall on the same trend with the lightest pions and kaons and whatnot. So we observe this significant scaling features, which is taken for evidence of thermalized partonic medium that hadronizes with coalescence. And even with D0, with this flow of D0 mesons, we have to see that the charm collectivity is also achieved in these collisions, and we can possibly even talk about thermalization that sets a very high bar for what the temperature of that medium is. Speaking of the temperature, it is very, very hot. We can actually not only see it through the thermalization, from this explosiveness, we can see from melting of the quarkonia, and this is one of the predicted QGP features and the QGP thermometers. So what we do here in this plot, and this is Atlas, CMS, and STAR, so again, variety of energies, same behavior. We're looking at so-called nuclear modification factor. And it's simply, you measure something in heavy ions, and you divide it by the same measurement in proton-proton reference, scaled by number of binary collision. So number of binary collision is essentially if your nuclear collision behave like incoherent proton-proton, so then you would get just simply a ratio of 1. These binary collisions typically calculated by the Glober model, but don't worry, we have now multiple cross-checks that we know what we're doing, because we can check it with colorless probes that do not interact with quark-gluon plasma, such as the W's, the isolated photons. So we know our scale. So when we take this ratio and walk in all the plots from left to right, you go from peripheral, barely glancing collisions to very central. We see that suppression, you fall farther and farther from 1 for upsilon states, upsilon 1, upsilon 2 and 3 combined here, same for star data. And now CMS for the first time ever observes upsilon 3s individually. This state is so melted that it took us several years of statistical data gathering to be able to place that point here. So how does it relate to the temperature? Well, these different quarkonia states, and we have same RA measurement for other species, they have different binding energies. So when you put it in a hot colored medium that creates this color screening based on the binding potential, you would expect this separation of the states or melting of the state happen at a different temperature. And the fact that we observe stronger suppression for a weaker bound state just tells us how hot that medium is. Finally, I could not avoid, this is actually doesn't connect well to my next part of the talk, but you cannot talk about QGP and not talk about jet quenching. This is that opacity to the hard penetrating probes, and this is what I do most for my own research, so I have to say a few words. So in the beginning of the jet quenching era, we started with just the RA, and then we went for jets and many other types of measurements. Same as for upsilon, you measure in heavy ions, particular species, or jet, or something, divide by pp, binary scaled reference. And what you see here, everything is suppressed below 1 significantly. And now if we study identified hadron species, we see that charm losing energy, B, the very, very heavy B, losing a lot of energy. We see here the B hadron reconstructed and J psi, non-proton J psi from B hadron decays. Everything is of the order of 2 at the least. We also see the trends that at mid PTs, we seem to see substantial flavor dependence, but charm is nearly as strongly suppressed as the light hadrons. And B is a little bit on a less suppressed side by this in, say, at 10 or 8 GeV, but by high PT, we go into the regime where the radiative energy loss dominates and everything, every quark species behaves or loses the energy of the same rate. Of course, this is not directly energy loss since the fragmentation comes to play. We don't have direct connection to identified particle PT and the parton momentum, but we can do jets. And jets is the closest connection we have to a parton energy. And here are the same. We see strong suppression for inclusive jets, for gamma tag jets. And we can follow different, with this jet quenching is not about just the suppression. We don't see them. We can study energy balance. We can now look for where does this energy go after our hard scattered probe tried to go through the QGP. We can look at the energy balance, as I said, for example, for gamma jet or Z jet events. So you take a colorless something to normalize your energy scale, and then you see what happened on the other side. Or we can study the energy flow, the change, the modification of fragmentation functions, of jet shapes, angularities, and so on and so forth. And we see a complex of modifications induced by the presence of quark-gluon plasma. All right, these are the pillars. How does it all connect to the DIS, and why would I go and do the DIS, or why should you, if you are a heavy ion physicist, do this? So heavy ion physics is more than colliding just 2 heavy ions. And in fact, we started using system size for control of different initial and final state effect. I explain it in a second. For a while ago, but it was simplistic and choppy picture when we began this quest. So we had proton-proton collisions, which we call, well, this is a reference. Oftentimes you'll hear vacuum reference, mainly for hard probes, vacuum fragmentation. We still do that. Why rely on even best tuned Monte Carlo generator if you can do the measurement at the same energy as your main study? And then the PA, when we got into the precision era, so now the cold nuclear matter, this is where the initial state effect that we realize, and well, there is a differences between the nuclei and the nucleon, and we wanna, if we do precision physics, we need to count account for the effects, for example, shadowing and anti-shadowing, and I'll talk about what those are in a moment. And then finally, of course, most of the time we spent on QGP, which we thought hot nuclear matter. We used centrality, that is the degree of an overlap, to how hot and how much of the plasma we create to essentially balance out the cold versus hot nuclear effect influences. However, as we study, as we carry out the program, this paradigm, this simplistic division start to change and blurring the edges of what cold, what hot, what's reference, because we discover a lot of interesting phenomena across the board in all of those systems, and I will argue that it has direct relevance for the physics of EIC and perhaps how we should tackle some of the open questions of the EIC physics. I'll go back to collective phenomena now in a small system. Remember, I showed you this very famous plot for heavy ion collisions. We've all done something like that. This is a long range reach correlations, and all was good because we said, well, this is a plasma, you see it, it's a very strong V2 of our explosive medium. And then we saw the same thing, well, historically, in proton-proton collisions at high multiplicity and p-lead collisions, our cold nuclear matter reference. And you see by naked eye, it looks, well, the amplitude, the magnitude is slightly different, but it looks exactly the same. And these long-range collective correlations nowhere in any single event generator for proton-proton is just nowhere to be found. However, the theory developments now tell us that they can get to this if we get this lumpy density variation in the transverse plane of our proton density at the x of, say, 10 to the minus 3. This is from Bjorn-Schenke. Which is, what is it as not connection to the TMDs? This is a transverse momentum distribution. So perhaps this is a non-traditional way to study the same thing and observe these distributions in a heavy ion traditional way. Of course, it impacts many things. Now, we already know that this lumpy state, we indeed can, we can model this in a small system. There is this, for those who follow the story, a special run was a trick in PA, DA, helium-3A. We see these components. This is a third Fourier term of this decomposition. Here we realize that also we need this, if we model it with a hydrodynamic evolution, as a small droplet of quark-gluon plasma, then you have to be very careful, including the 3+1 hydro, because it's no longer boost invariant as our large colliding things at mid rapidity, and then incorporation of that allows to reproduce the data. But then questions remain to me personally, how something that tiny, especially go back to PP, how can something that tiny reach an equilibrium very quickly to produce the droplet of plasma? And so really, do we see a manifestation of some new phenomena, or is it just really something that we already thought of and just didn't think of the implication for correlation of the type, like the color glass condensate? Now, of course, any model that would describe one way or another, do we do the small droplet? Do we go for the color glass condensate description? Another blow to sort of how different the systems, the simple and the quark-gluon plasma forming system should be, is that constituent quark scaling. So now we do the same with identified particles in p-lead, and the same thing happens. We see this baryon meson grouping, and lo and behold, something, I don't have D0 here, but I have prom J psi for your charm, and it flows. So this is really puzzling for sort of this paradigm that we're dealing with a cold nuclear matter in one case and a hot nuclear matter in the other case. And we really have to carefully understand our nuclear matter. Now, it's getting worse. Now we go into EIC physics, ultra-peripheral events. So we're really looking at gamma lead. So this is no different than, this is a DIS other than we didn't have electron to strike it. And we do this azimuthal decomposition of final state particles, and we see the V2, these are the red points that follow this high multiplicity PP and not far off from the P lead events. So now you have your gamma lead that flows. And here the competing interpretation, whether we underestimated of the raw production, and this raw is actually a dominant diagram here, and you're really looking at raw lead interaction, and then maybe it's not so different from P-lead interaction, which is, we already sort of give up, okay, it forms something that flows. Or look at this green line, this is that saturated color glass condensate prediction that does capture the points in magnitude. These are LHC Atlas data, CMS sees similar thing, and I'm glad to see that now at REEC, this has came out at just this fall. You could see this decomposition of the correlation from gamma gold events. And first you could see by eye, this flattening over here. This is a positive V2 contribution in there. Still handling the non-flow subtraction. This is a subtle issue. So we'll see. Now next, you could think, well, certainly gamma A events, it's a small system. You have to conserve transverse momentum, and then correlations can pop out from just pure momentum conservation, right? If I have a particle here, I would have to have a particle here. That's your V2. Then maybe it's a different sort of correlations than we just, Fourier transform it and look at that. And of course, it's strange that it conspires to have the same trend, but things can happen. So the test is, well, if it is a collective expansion, such as hydro expansion, then it should not be only azimuthal anisotropy. The whole thing should expand radially. So, and then Atlas used the same data looking at the min PT, because the min PT is characterization of this radial explosion, expansion, right? So if everything is boosted outwards, you shift to higher transverse momentum. So they study, this is these data points in red. You see here the backwards, the lead going and forward rapidities in the model of the gamma lead, the best that we have, DPM jet. And of course, that's news. It's off by substantial amount from a model prediction. And then we compare, or they compare, to the P-lead events, where we already have seen many evidence of collective behavior from this constituent quark scaling, multiple harmonic, multi-particle correlations, and they just line up so perfectly that I cannot look at this plot. So this really looks at the very least, it's consistent with both the azimuthal, the elliptic flow, and the radial flow. If it quacks like a duck, walks like a duck, it's very hard to explain away the presence of these seemingly collective effects and seemingly should not be behaving collectively systems. So I ask myself, when does it stop, and why do we see these collective things? And I thought last year that I have an answer for you, that we know where to draw the line in the sand. And that would be the reanalysis of Zeus data EP that published in 2020. Lucky everyone brief with ease, no ridges and high multiplicity events. And then Aleph reanalysis, same year, E plus and minus, minimum bias data, also said no ridges. This is an example described by Monte Carlo. We said, okay, we know it's something with LHC data, something is wrong. And then another group of people, it's about to get published, selected Aleph. It's instead of going for minimum bias, they took high multiplicity, and that's an event sample enhanced with E plus and minus going into W's, pair of W's. And for those of you who, like me, stare at those plots, that's there. So that's there. And then they look at this point. So you look in here, it's a V2 of data minus V2 of Monte Carlo, because here you do have momentum conserving terms, so you have to account for that. And when you do that for this high multiplicity PP, our CMS data, excess in E plus and minus and PP over the Monte Carlo that does not have this ridge is the same. So folks, if you're preparing for doing analysis at EIC, we will be looking at ridges there. I think we can safely predict it at this point already. So more direct connections from PA to EA is, of course, the initial state studies, as I already said. The questions for us from heavy ion is the nature of this initial state. We all know we get to low X gluons. We looked at this diagram, or one version of it in Raju's talk yesterday. But when we get there, when do we get there and how do we deal with QGP droplet when we see this interesting correlation? So post-collision dynamics versus are we really in saturated color glass condensate state that is already correlated, and that's why the same trend, same systematic just keeps popping out of different systems, the moment that you poke at it. First studies that we can sort of collaborate between heavy ion and DIS people is the first order of business is nuclear parton distribution function. They are modified. So what is it for us? You could see here a sketch of the ratio. This is how the, at least theory people, this is from EPPS 16. So modification of nuclear distribution in nuclear versus in free nucleon. And you could see the deviations from 1, for example, in small x shadowing regime. It's 40%. We in a precision studies of QGP, we cannot afford 40% uncertainties in our initial state. So, and another interesting thing is that in the DIS experiments, you already studied the energy loss. We study energy loss. So it's possible to have it in a cold nuclear matter, in a hot nuclear matter. We certainly better know what happens where. So this is a plot from the EIC studies. I draw your attention what we expect to have. The impact of measurements here, the inclusive cross-sections measurements. I particularly want to draw your attention to this 10 GeV scale, going down to 10 to the minus 4. Inclusive and charm collectively shrink these uncertainties a lot. And of course, this has no complications as we have to deal with in PA because we don't have resolved kinematics. However, we would love to have least uncertainties than a 40% scale because we need to understand initial state. We need our jet quenching baseline, and of course, gluon saturation. If you want to understand, it's so this 40% really matters. But in the meantime, while we're waiting for EIC to come on board, we already doing something towards understanding of initial state, and that's of course here LHCb at LHC particularly shines. Although I should say I just don't have a time to do an overview of all the experimental data, so this one I particularly want to highlight. This LHCb D0 forward measurements. You see the data points. Look at the theory uncertainties. This is coming from these uncertainties in NPDF I showed you in the previous slide. And from this particular set of data points plus CMS dijet measurements that we published about 7 or 8 years ago, this EPPS 16 previous uncertainties shrink already in the set at the same 10 GeV scale quite dramatically. So we can start doing, placing new constraint and lead to substantial reduction of uncertainties already at the low X domain previously just envisioned to covered by EIC alone. It's not without a struggle. For example, same LHCb, you could see here charged hadrons and Ramanujan measurements. I'll show you just one slide next. I'm not going to talk. Identified direct photons, jet measurements, you name it. Look, for example, here, again, experimental uncertainties versus theory uncertainties. Point from here, we, of course, need badly improvement on the modeling on the nuclear PDF. Generally, the trends that suppression at forward rapidities is the top panels, everyone expected. We see this is a low X domain, color glass condensate gets the trends, not quite the points. Backward regime, this is most difficult. So the data show enhancement consistently, show a variety of plots there. This yellow curve, this is a PQCT calculations with a higher twist. They are tuned to as Phoenix data, and then you do the projections to LHC, and it's completely missed the trend. So we know that we miss some components in our NPDF modeling, and hopefully we will be able to address some of that with more and more differential data. Again, this one is just that we keep working on the same ground that is of interest to AIC. Not going to give more credit to LHCb, that's just enough. But generally, forward suppression, backward enhancement, perhaps only the D sub S here is consistent with one, but perhaps not enhanced. Now, let's switch gears. So I talk about some additional common aspects that are of interest for both. Hadronization, hadronization is the flip side of confinement. If you don't understand hadronization, we cannot talk about understanding confinement. On the plots here is strangeness excitation functions and baryon to meson ratio. Why? Well, they were proposed as the signatures of the QGP early on. And then we, of course, seen the strangeness, for example, enhancement in quark-gluon plasma. I said, this is it. But now, just like with these flows, we have from proton-proton to p-lead to lead-lead at LHC, everything behaves very smoothly and enhances strongly. So this multiplicity dependent enhancement are actually of very similar level if you just slice at a given multiplicity, and the models are way off. Again, now simple Pavia, the tunes that we know and love do not reproduce nearly orders of magnitude away from this strangeness enhancement. You can play with color reconnections and get roughly closely there, but not quite. Second topics here, charm sector. So baryon enhancement in all sectors seen is evidence for this protonic recombination or hadronization from coalescence. We see it here. Problem is we again see it in PP. And in this PP measured lambda C over D0, the problem is we way off this pink line, which is a Pavia, but also the E plus, E minus, what color is that? So E plus, E minus reference. So we have some indication that we have a lot more charm and a lot more charm baryons. And then Alice went on to the quest and measured fragmentation fractions for all what they could, different charm species. And I understand that's a very small plot. I cannot zoom it on the whole slide. I wouldn't make it. But look at the box point and the empty points. The box points are all Alice points. The points without the boxes are hero points, lab points, B factories points. And you see 30% off, 50% off, and factors of off. So what we see is that charm fragmentation function appear to be non-universal. And then if fragmentation is non-universal, all our idea of factorization is under the question, and that impacts a lot of fields and would require detailed understanding so that we can piece it back together. Almost at the end of my talk with 1 minute, so if I'm gonna make it. So we, of course, study, as I said, energy loss in a hot nuclear matter. These measurements of RAA, the nuclear modification factors, is important for understanding energy loss in the cold nuclear matter. So here is some data, for example, from Hermes, where we see this change for different changes, different suppression levels for different nuclei. So the question stays whether we're dealing with energy loss, that is, you have energy loss on protonic level, and hadronization occurs later after it escapes the medium, or it hadronizes inside, and it's a pre-hadron that loses, or pre-hadron that loses energy through nucleon scattering interactions. So that tells us about timeline of hadronization. And what we can do is just augment this type of studies expected at the EIC for variety beam species and energies with a matching sets, or at least as big a variation as we can for a PA reference. We're also doing something that goes to hadronic structure, for, where we can use a combination of cold versus hot nuclear matter to understand the internal structure of such exotic states. For example, both LHCb and CMS observed this X3872. We don't know yet if it is a tetraquark or weakly bound molecule, and looking at its survival rate, that is PP versus PA or EA, we will be able to tell more about its composition. This topic Raju introduced yesterday, and the only reason I added it into the slide is we talk about dijet and seeing the suppression, like here in dihadron correlation, as a possible signature for saturation. However, perhaps, again, we should take a holistic approach and look at additional, maybe not as expected or not first thought, probes of saturation. So here is a very recent publication from CMS on coherent JSI photo production. This is from ultraperipheral collisions that is used to probe the small x gluonic structure of lead nuclei. So what you see here is a cross section as the center of mass gamma n pair. So, and the cross section turns over very quickly. So this grows with like W to the fourth, to the power of fourth, until it saturates, plateauing at about 50 or 40. Of course, this is a log scale, so it's not an entirely flat line, but it's a very slow linear growth after that. So then the question is it really this change of the regime signifies us reaching that saturated gluon state, or we're hitting some limit of the strongest absorption where we are in a black disk regime, and essentially only the side, the outside outline of the nuclei contributes to the cross section. Well, naturally, when we're trying to convert it to this nuclear modification of the PDFs, there is no models that captures the data points. Notice that there are ALICE measurements here as well in both cases. But of course, this trend is now neither of the models incorporates neither the CGC here or this black disk strong absorption limit. So I'm not completely out of time, so I'll leave the detectors alone and just say that we are studied quark gluon plasma, making it in the lab and looking at this property from early 2000s. So it's now not 20, soon going to be 25 years. I will be updating the text here. We in the era of precision studies, and that we provide many new constraints, not only on the QGP properties, but also at nuclear properties and the subnucleonic degrees of freedom in ways that we didn't expect we will. And that has connections to many other fields, including to the deep inelastic scattering. So while EIC is still under construction, we hope to provide new experimental input in form of these novel phenomena that are relevant for understanding the ground state of our nuclear, so to say, and also shaping this program of EIC. And of course, besides that I run out of time to talk, there is a lot of synergy in detector developments for heavy ion physics, for high energy physics, and that immediately translates into the developments for the EIC, and we hope to also capitalize more on this synergy and contribute to EIC success. Thank you.
Okay, great. Thanks a lot for the very nice talk. We still have time for some questions.
Thank you. I have a provocative question. Thank you for the talk, but I have a provocative question. But I first have to confess that I have in the background of my mind a sort of bias towards this, because as you nicely described at the beginning of your talk, there are so many steps in describing the evolution of the system in these hard collisions that, I mean, I think it's a hard time to connect an observable to the information that we are after about the hadronic structure, microscopic structure of our system. So so you say that now the heavy ion collisions are in the era of precision studies. Precision studies to me means that you have identified the clean observables that you want to study with precision. Observable that from which you want to make deduction on the status of what's happening and what you are after. Now, if you go, for example, to slide 22, you were describing the change of picture here that, you know, the strangest, for example, this is just an example, the strangest and baryon to meson enhancement was all, since long time, considered as an evidence of the quark-gluon plasma signature, and now it's not, because of the results you're showing. So the question is there a clean observable that tells us, for example, that quark-gluon plasma is happening, or for example, another kind of observable is we are after is about saturation. I remember I had a conversation with Raju some time ago, and he was telling me that the best thing that the best observable they had in mind at the time was the diffractive production of JPSI, while you are mentioning different observable. So again, the question, is there a clean observable we are after?
So I do believe that in either of the cases, there will be not a single smoking gun. We already, been there, done that, and this is not going to work. I think I take an example personally from the exercise that I observed as a, then still young scientist. The white papers of the RIC collaborations on the discovery of the quark-gluon plasma, which none of them said discovery, but it was a critical assessment of all the observations from the 4 RIC experiments to date and what sort of, how they could be interpreted as a coherent picture. So from the perspective of the quark-gluon plasma, when you're dealing with the heavy ion side, it is very coherent. We believe we understand it very well. We have small dials, we can probe it sort of in a controlled way, and it responds now predictably. It is unexpected development for the field to observe all these phenomena in sort of a no man's land that we didn't expect to be touching for quark-gluon plasma study. So I believe, well, from my perspective, it's not yet consensus in the field what's happening there, right? It's there is many of my colleagues who are proponents of the small QGP droplet. You can go and see there are Nature paper on that domain. Then I say, you'll have to go to EP and say, well, and there too, right? And that's where I have start having bigger and bigger problem. So that we'll have to still reconcile with, but I don't think it's going to be a single measurement. So that is unfortunate. Otherwise, it would be quick to be done.
Yeah, so Olga, thank you for the excellent talk, really nice. And it's a slide I wanted also to ask something. So you compare, for example, this charm, and there's this conclusion, or factorization is broken, or it's not universal, whatever. Has been considered that the feed down to these different mesons is energy dependent? because that is something which it becomes harder and harder phase space if you are at lower energy to produce, for example, heavy mesons, which then produce D0 or things like this. But in your case, of course, with the Alice, you are at a phase space where you can easily do this. And I think there's often what I find a bit difficult is there are strong conclusions taken without really looking in all directions. And an energy dependence of the feed down is a simple one.
So that is to my Alice colleagues. So of course they say they study the feed downs, those the systematic uncertainties on the points, right? So they are the only one at LHC who can measure the most identified particle species. So perhaps that's the most reliable that we have. But I agree with the point that this is, or perhaps you're nicely pointing to me that I should put a question mark at my factorization,
which is
non-universal.
Fine. That's okay. But it's the same for
Point
strangeness.
taking, but yes.
If I can, we have seen a strangeness suppression, for example, is energy dependent. At Hermes, strangeness is much more suppressed than it is at Rick or so, where you get to the Bronsert. And okay, here you have the baryons and some other ones which are different. So that is not something which has been measured, but energy dependences on some of the things is not unknown and has been seen before. And maybe that is something which needs to be taken into account and then also modeled in the Monte Carlos.
That would be, LHCb would be good. Monte Carlo is difficult because Monte Carlo misses it but by order of magnitude when you go to multiple. But in Monte Carlo, worse, in Monte Carlo, for example, even for strangeness, there is no multiplicity dependence. So you see this like a pure PFA, the lines are flat. You don't get any sort of enhancement.
Okay, one more quick question from Alessandro, and then
thank you for the very
on.
nice talk. And you mentioned TMDs a couple of times, and that, of course, triggered my curiosity. I wanted just to know first if these ideas apply. You think they apply only to gluon TMDs? First question, and the second question, if you can explain me what you expected to find and why it is these unexpected findings could be related to TMDs.
The connection to TMD comes from our theory friends that say if they model initial proton, you could see here this snatches. So this is a proton density distribution. They do this lumpy, and it's gluons at this stage. Then they can get to something that looks like this collective ridge. So because otherwise, if you do point-like, so in valence quark scenario where you have scattering, some string breaking, you do not get the entire event essentially across 4 units of rapidity coherently having azimuthal anisotropy across your phi. So why I think gluons? Because it has to be many, right? Because it involves soft particle production, the bulk, the entire things, right? Not the hard scattering one. So I don't think it's going to be in there. I'm not sure we can do the quark TMDs that way. But for example, however they had to tune these density fluctuations to capture the correlations, that's sort of that same way we can talk about the width of these profiles. It is, well, right, but it is spatial distribution, correct. But when I think about spatial and you have TMDs as in where you in transverse momentum and location with, full 3-dimensional modeling. So perhaps TMDs is momentum part, but I'm thinking of where you end up with that.
So we're a little behind. We need to set up the next talk, so we have time for one more question, and then we'll move on.
Thanks for the very nice talk.
Oh, thank you.
And when you mention about this QGP droplet in proton-proton, so hydrodynamics doesn't always mean that it has to thermalize. It can also happen that it is isotropizing, and that's how one can apply hydrodynamics in that case.
Mm-hmm.
So how do you distinguish between these two scenarios, whether they really thermalize or it is just...
So to me, which is not fully, so for protons is, we'll have to see when this data will come out. What it comes together with is individual, this particle species. When you measure PIDV2 and you start seeing baryon meson, right? So it behaves collectively on the quark level, so on protonic level, right? So that's where, and then forms from this have to be coalescence picture so that we have this constituent quark scaling. So I have to assume that it behaves as a medium with a common temperature so that it can actually, you know, in the statistical manner, hadronize into 2 and 3 triplets with carrying twice and 3 times the medium flow. So
but,
I think
when people discuss about statistical hadronization also visible in E plus E minus collisions, then what is that statistical hadronization? Is it like a thermal model or it's like just a statistical production of hadrons?
No, this is different. In statistical hadronization, this is not, we're talking about bulk particle production. Here we're talking about this flow behavior as a function of PT that is grouping into baryon and mesons, where it's explicitly 2 and 3. Statistical hadronization, indeed, you can have sort of a, because you study it an ensemble average where you aggregate across multiple events, you can have that essentially on an ensemble of your total events appearing statistical. But that's different from what I'm talking about here, where you have baryon meson grouping, and it comes from individual events because you have in-event correlation, not aggregated.
Okay. All right. Thanks so much again for the talk, Olga.
Oh, yeah. I'm stealing the mic.